All right, let's get started. So, today I'd like to talk to you about arc length. Now, as a reminder, this is Math 52, Section 4, of Professor Ellis's class. Your SI Jack Quirk. And today, like I mentioned earlier, we will be covering arc length. So, before we jump right into problems, it's important to remember the definition of arc length, the given function, which is the integral from whatever the bounds are of the square root of 1 plus f prime of x squared dx if your function is f of x. So, if we look at the given problem, say y equals 1 plus 6 to the 3 halves, and we want to solve this for 0 is less than or equal to x is less than or equal to 1. Then we take our derivative, which is y prime, which is basic power rule. We have, there should be an x there. Sorry about that. That makes sense. Okay, so, right, the derivative of y is going to be multiplied by 3 halves, and we get 9 square root of x. Okay, so we plug this into our arc length formula, and we get the integral from a to b, a being 0, b being 1, of the square root of 1 plus 9 root x squared dx. Now this is equal to the integral from 0 to 1 of the square root of 1 plus 81 x dx. That's just simplifying the squared portion of the square. So, moving on, we're going to evaluate this integral from 0 to 1, and we can think of it as 1 plus 81x raised to the 1/2 dx, which makes it a little more obvious that what we're dealing with here is a u substitution. So u is going to be equal to 1 plus 81x du is going to be equal to 81 dx. So dx is going to be du over 81. So set this in, and we get 1 over 81 times the integral, and this time we're going to plug in for u. So 1 plus 81 times 1 is 82, and 1 plus 81 times 0 is just 1. And we're going to evaluate this at u raised to the 1/2 du. And I'll come down to the bottom of the screen here for the evaluation of this integral, and it's going to come out to be 1 over 81, evaluated from 1 to 82, of u to the 3 halves, divided by 3 halves, which is just times 2/3. And now if we plug this in and simplify, so we're going to have this equal to 1 over 81, 2 times the and we can pull the 2/3 out, actually. It's probably a better step in terms of the math. So we'll just pull the 2/3 out. 2 over 81 times 3 multiplied by 82 raised to the 3 halves minus 1. Now, we could choose to try and evaluate this, but for simplicity's sake, we're just going to leave it in this exact format. So that's our first problem. As you can see, these arc length problems are relatively straightforward as long as we can remember the integration and derivation concepts. Now, this next problem we'll be dealing with has a bit of review for you in terms of factoring. It would be a little confusing if we had forgotten how to use factoring methods, but let's take a look. So this case, and it's also important to remember that these functions can be in terms of x and y. It's basically, are you taking the rectangles lengthwise or widthwise in terms of your integration? So let's say, for sake of example, we have x is equal to y to the fourth over 8 plus 1 over 4y raised to the second. And we want to find the arc length on the interval with 1 that's less than or equal to y is less than or equal to 2. Now in this case, it's important to remember that we can also write the arc length function as the integral from, let's say, c to d of the square root of 1 plus dx dy squared, taken with respect to y. So basically, we have the exact same formula, just know that it can be applied to either x or y. So let's take our x prime. It's going to be equal to y to the third over 2 minus 1 over 2y to the third. Okay, so we'll plug that into our length formula, and it's going to be equal to the integral from 1 to 2 square root of 1 plus, this is where it gets a little complicated, y to the third over 2 minus 1 over 2y to the third squared dy. So the only course of simplification is to FOIL this out. So this is going to be equal to the integral from 1 to 2 square root of 1 plus, and the FOIL of this we have y to the sixth over 4 minus 1/2 plus 1 over 4y to the sixth, taken with respect to dy. All right, so what does this mean? Well, if we simplify our expression within the radical, we get length is equal to the integral from 1 to 2 square root of, simplifying the inner portion of the integral, y to the sixth over 4 plus 1 over 4y to the sixth plus 1/2. Now, how can we FOIL it? How can we simplify this? Well, it turns out that this function is actually a perfect square function. We see that this can be simplified as the integral from 1 to 2 of the square root of the following. Y to the third over 2 plus 1 over 2y to the third squared. And if you FOIL that out, you'll see that it simplifies to our inner expression. Square and square root cancels, and we get the integral from 1 to 2 of y to the third over 2 plus 1 over 2y to the third dy. Alright, so evaluate the integral, 1 to 2, y to the fourth over 8 minus 1 over 8y to the fourth, which is going to be equal 2 minus 1 over 8 times 16 minus 1/8 minus 1/8, which cancels itself out. Simplify the expression. Our length is equal to 2 minus 1 over 128, or 255 over 128. So, as you can see, this problem would have been a little tricky if not for the factoring. Otherwise, it really wouldn't have simplified to anything rational. But just got to keep all the techniques in mind when we're looking at these problems. Got one more to show you before we finish up for today. Afterwards, we'll have time for general questions about the material or anything that came up during this lecture. Okay, there we go. We have y is equal to the ln of secant x. Ooh, trig functions. Arc length evaluated from 0 less than or equal to x less than or equal to pi over 4. So how are we going to do this? Well, let's just start it out like a normal arc length problem. Y prime is equal to 1 over secant x times the derivative of secant x, which is secant x tangent x, which simplifies to tangent x. So our arc length is going to be a simple integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx, which of course simplifies 0 pi over 4 to, remember our trig identities, 1 plus tangent squared x is equal to secant squared x, which squared and square roots cancel, and we arrive at 0 to pi over 4 of secant x. This integral can get a little complicated, but it's in our table, so we can just reference that. Evaluated, this integral comes out to be from 0 to pi over 4 of the ln, absolute value, secant x plus tangent x. So the secant of pi over 4 is going up to 1, because secant is 1 over, oh, no, I'm sorry about that. That's going to be 2 over root 2, which, with 2 times root 2 over 2, so it's going to come out to root 2. Okay, sorry about that, folks. So we have the ln of root 2 plus evaluated at tangent, pi over 4, evaluated at pi over 4, the tangent of x is just 1. And then we have minus ln secant of 0, 1 over cosine of 0, 1 over 1 is 1, plus tangent at 0, sine over cosine, 0 over 1 is 0. Obvious there. Ln of 1 is just 0, so that cancels out. And our final arc length is the ln absolute value root 2 plus 1. So there you have it. That's arc length in a nutshell for you. If you have any questions, feel free to come by. And that should do it. Thank you for attending.